All right, welcome back. So this is another ALEKS topic called Using the Second Law to Predict Spontaneous Change. And this topic is a little bit more complicated than it might just originally look. And I think there's a lot of good conceptual understanding that can be gained here. So I'm going to go ahead and go through two different sets of this question. We get exposed to a variety of different ways the question is going to be asked. So yeah, let's go and get started. The first thing that we need to do is sort of understand what this question is really asking. And this key word here, spontaneous, is really the key word. So if we see the word, or it's asking about, is the reaction going to be spontaneous? We need to be thinking about the equation delta G equals delta H minus T delta S. So this Gibbs free energy equation, when delta G is equal to negative, when it's a negative delta G, that means the reaction is going to be spontaneous. And that's really what we're going to be looking for as we're doing this topic. We're going to be looking for, well, based off of what these changes are, do I see a negative delta G, a positive delta G, or a delta G that I'm not sure? That's going to be, we can't decide with the information that's given. So so let's go ahead and do the first example. The first thing that we're going to be doing, what we're really going to be looking for, is picking out the delta H and the delta S information from the change that's given. So if you see the word exothermic, well, right away we know that delta H is going to be negative. That's the definition of an exothermic reaction. And then in this case, I've got 2 moles of gas turning into 4 moles of gas. 2 moles are turned into 4 moles. That means my delta S is going to be equal to positive. That's an increase in entropy. And both of those, I sort of right off the bat know, are favorable for a spontaneous reaction. An exothermic reaction, right, it's going to give off energy. Increase in entropy is also going to be favorable. So I sort of know that this one's going to be a yes right away, but what we should do is we should consider what the implications of these signs are for my Gibbs free energy equation. So delta G equals delta H, lots of deltas in this, minus T delta S. If I have a negative delta H and then I subtract a positive delta S, then that means that overall this is just going to be negative, and then it's going to get even more negative, right? If we're subtracting a positive value, it's going to make it even more negative. So both of these are going to be sort of contributing or favorable for this delta G to be overall negative. Now, I've made a table here that is going to sort of go through or explain all of the different combinations. If I've got an exothermic reaction and I've got an increase in entropy or a decrease in entropy, if I've got an endothermic reaction and I've got an increase in entropy or a decrease in entropy, these are going to be sort of the results of those different signs for my delta H and my delta S. So this first one, this is what we saw here. And under these conditions, this reaction is always going to be spontaneous no matter what the temperature is. So if we see a negative and a positive, then we know that this is going to be a reaction that's always spontaneous. If we see something that's different, then we're going to sort of have something that's different. So let's go ahead and use this to go through the rest of these examples. So the first one, or the next one, says endothermic, therefore delta H is going to be positive. And then 4 moles of gas are going to turn into 2 moles of gas. So in that case, our delta S is going to be negative. So if we go from more moles of gas down to 2 moles of gas, we're going to be decreasing our entropy. And then we've got an endothermic reaction. So this is actually the exact opposite of our first case. So I know that both of these are unfavorable. Overall, it's going to be a no. That's also our bottom sort of example here. If I've got a positive delta H and a negative delta S, under all conditions, this is going to be a non-spontaneous reaction. We're starting out with a positive value here. We're going to subtract a negative, so subtracting a negative is adding. Therefore, we're always going to be non-spontaneous, so that reaction is never going to be spontaneous. And then if it's a sometimes, that's going to be based off of the temperature. So if we end up with one of these sometimes examples, then we're going to choose can't decide. Okay, a gas expands without absorbing or releasing heat. Just wanted to make sure I had the right thing there. Sorry about that. So a gas expands without absorbing or releasing heat. So a gas expands, so then that means our delta S is going to be positive. It's expanding, it's got more ways that it can arrange. An increase in volume, that would be an increase in entropy as well, without absorbing or releasing heat. So we're not given any information about our I guess we're told that it's not really, you know, exothermic or endothermic. The delta H we would say is negative, or excuse me, is 0 without absorbing or releasing heat. So what I would say that this means is delta H equals 0. It's not releasing heat, it's not absorbing heat, it's not really doing anything. So we've got 0, and then we could say we're subtracting a positive value. And since we're subtracting a positive value, then that means it's going to be spontaneous. That means that, you know, this doesn't necessarily fit in one of these, but if we think about our delta G equals delta H minus T delta S, if this is 0, we subtract, our temperature is going to be positive times a positive. Overall, we're subtracting a positive value, so our delta G should end up being negative in this case, so that would be spontaneous. Okay, let's do one more example, or one more set of examples, I guess. We'll keep our little cheat sheet here. Okay, so the next one, a solid precipitates from a solution. That means that delta S is going to be negative. So a solid precipitates from a solution. We're decreasing the entropy, absorbing heat as it does so. So absorbing heat, delta H, is going to equal positive. So in this case, positive delta H, negative delta S, always non-spontaneous. So that's going to be a no. A chemical reaction between two liquids creates gaseous products. So in this case, our delta S equals positive, and we don't have any information at all about our delta H. So in this case, we can't decide because we don't know what's going on with our delta H. So if our delta H is negative or if our delta H is positive, we don't know. So it's not told, you know, we're not given any information about that, so we just can't decide on that one. Two liquids mix, neither absorbing nor releasing heat. So this is very similar to the other one. That's why I was looking at it earlier. Delta S equals positive. So we're mixing the liquids together, neither absorbing nor releasing heat. That means delta H is equal to 0. Just like before, that means that this is going to be spontaneous because the positive entropy change, that's going to contribute to the spontaneity. And if our delta H is 0, right, neither absorbing nor releasing heat, our delta H is not contributing, then that means that overall this would be a negative delta G. So really, you know, all we're looking for is delta G going to be negative based off of the conditions that we see here. If you end up with, I guess I didn't in this video, end up with any of these negative or positive situations, for this case, we're not going to know. So these, you know, if it says sometimes, that's going to be can't decide as well, just like this middle one, where we're not given that information about delta H, so we don't know necessarily, you know, is it going to be spontaneous or not. So, all right, hopefully that helps. Let me know if there's anything that's unclear about that video. Cheers.